Hello, this is Dr. James Camp from Lee College in Baytown, Texas. And this is my second in my series of videos starting off in C++. Today we're going to talk about mathematical functions in C++ and a little bit of how to format your output in tables and significant figures and such. So we're going to be doing two projects today. One, we're going to be printing a logarithmic scale table, and the other is we're going to be printing a table of trig functions. So why a logarithmic scale table? Sometimes values increase exponentially. The infection rates of COVID, for example. And so we want to plot them on a logarithmic scale instead of plotting them on a standard scale. One example of a log scale is what I call the 1, 2, 5 scale, where you plot evenly spaced 1 and then 2 and then 5 and then 10, 20, 50, 100, and you keep going if you want. If this looks familiar to you, this is actually the scale that U.S. currency is based on. We have dollar bills, $2 bills, though they're not used that much, 5s, 10s, 20s, 50s, etc. So let's write a quick C++ program to find out if these numbers are actually evenly spaced on a logarithmic scale. In other words, we're going to calculate the base 10 log of each number and see if those base 10 logs are evenly spaced out. Okay, first, this should look somewhat familiar to you. We need to set up our program the way we always do. We're going to include IO streams so that we can have input-output functions. We're going to use namespace standard. We're going to have a main function. But we're going to add one thing to our list this time. We're going to add the CMath library. We're going to include CMath. All of the C++ libraries that start with C have been brought over almost without any modification from the C standard library. Okay, so if you're writing an actual C, you would include math.h. In C++, we call it CMath. As you might guess, it provides a whole bunch of mathematical functions, your trig functions and your log functions, exponential functions, hyperbolic functions, all sorts of mathematical functions. You can find a reference at c++.com that will explain all of the CMath functions, what they do, and what you can use them for. We're also going to add the IOManip library to format our output. IOManip provides output manipulators that the set width manipulator lets you line up your output in columns, and the set precision operator lets you specify how many figures you want to round floating point numbers to. Okay, so we're going to write a main function. We're going to calculate and print the log of each of our scale numbers. First, we're going to print some column headings to help interpret the output. So we're going to use the set width manipulator here for the first time. Set width is an output manipulator. You put in parentheses the number of spaces that you want the column to be, how many spaces wide you want that column to be, and it will print only the next output field in a field that number of spaces wide. So we're going to set width 8 for the scale number field, and we're going to set width 12 for the common log field, mostly to fit in the size of the column headings. Next, we're going to indicate a preference for 3 significant figures. C++ defaults to 6 significant figures, and that's good for some cases, but in this case, I don't want to be distracted by extra figures after the decimal point, so I want it to round to 3. And then finally, we're going to print the output for each of the scale numbers. You can see we've got set width 8, and then we print the scale number, and then we have set width 12, and we print log 10 of 1, 2, 5, 10, 20, 50, 100. Now log 10 is a function. That's a pre-written chunk of code that does a task for you. Okay. Functions typically take a number in parentheses. Sometimes they take several parameters in parentheses. We'll study functions in more detail later. And a mathematical function at least, is going to take a number in parentheses and it's going to return a calculated value. So essentially, that little chunk of code is going to be replaced by the log base 10 of 100. Now, why log 10 and not just log? It turns out that the natural logarithm is so common in science and math applications that the writers of the C standard library made the phrase log, the function log, equal the natural logarithm. And so log 10 is the common log, what you usually mean when you just say log. Okay, so here's what the output of our little program does. It shows that 1 has a log of 0, 2 has a log of 0.301, 5 has a log of 0.699, and they step up to, 20 is 1.3, 50 is 1.7. So you can see that these are not quite evenly spaced. We go to 0.3 and then 0.7 and then 1, 1.3, 1.7, and 2. It's close, but it's not quite a perfect log scale. Okay, let's try instead setting perfect log spacings every 0.333, say. Okay, every third, split the range into thirds. And then let's try converting them back to normal space and see what our, the markings on our log scale should be. Now, that means we're going to do the inverse operation of log. We're going to start with things in log space and transform them back to normal space. And the inverse of log is 10 to the x. Now, C++ has no 10 to the x operator. It has no exponentiation operator. So we're going to use the POW function instead. Okay, POW takes a base, comma, exponent in its parentheses. We'll see how that looks in just a second. So now the heart of our code will look like this. We'll have set width 8 for the first column, and we'll print 0, 0.333, 0.667, 1, 1.333, 1.667, 2. Then we'll set width 12 for the next column, and there we're going to print POW 10, comma, and whatever our power is. Okay, so 10 to the 0, 10 to the 0.333, 10 to the 1.333, all the way up to 10 to the 2, which we know should be 100. So here's what our output looks like from this little program. In log space, we have 0, 0.333, 0.667, 1, 1.33, 1.67, 2. In normal space, we have 1, 2.15, 4.65, 10, 21.5, 46.5, 100. So you can see our 125 was a rounding error essentially on what the real log scale should be. We should have 1 and then 2.15, then 4.65. If we want a truly even logarithmic scale. Okay, moving right along, our other project for this lab is going to be printing a trig table. Okay, people doing mathematical analysis or just trying to build a triangular wheelchair ramp or something often want to know all 3 of the trigonometric ratios for an angle. Okay, this is easy if you know how to program a computer. We want the user to enter an angle in degrees and have the computer print the 3 trig ratios, sine, cos, tan. The problem is that the user wants to enter an angle in degrees because most users in America think in degrees. Very few people think in radians. But the CMath trig functions, this is true for pretty much all computer programs, Microsoft Excel, R, Python, C, all of those trig functions expect angles in radians. Okay. Fortunately, there's an easy conversion. The angle in radians is equal to the angle in degrees times pi over 180. Okay, you divide by half a circle, 180 degrees, and multiply by half a circle in radians, pi. Okay, so what value do we use for pi? We could just come up out of the top of our head, well, I know 3.14159. But is that precise enough to get the right answer from these trig functions? Maybe it is, maybe it isn't, but CMath provides a high precision pi constant with a dozen or more digits called M, capital M underscore capital pi. Stands for MathPI. Okay. But MathPI, for reasons that I have never figured out, is turned off by default in case, the average person wants to define their own pi, I guess. So you have to turn it on using a pound define operation, which looks like this. You type the word pound define in lowercase, and then in all uppercase you type use math defines, but you start with an underscore. So it's underscore use underscore math underscore defines. Now, through experimentation, I've determined that this use math defines has to be the very first line of your code. It has to happen before any pound includes. Okay, so your header section, the very top of your code, should now look like this: pound define, use math defines, then pound include IOStream, pound include IOManip, pound include CMath. Okay, so let's get to writing the program. We want the user to be able to enter an angle with fractional degrees, such as, say, 22.5. So we will use a double type variable to allow the decimal point. We'll get more into the differences between int and double next time, lesson 3. So I'm just going to say for right now that we're going to use a double type variable. So we declare the variable double angle degree. Now we will use the cn object, okay, and the greater than input operator to read in the angle. Again, we'll talk about that in more detail in lesson 3, so I'm not going to spend a lot of time on it here. In short, cn stands for console input, and the greater operator pulls a single input value out of your console input that tries to match the type of the variable that you're reading input for. Okay, but before we can read an input, we have to prompt the user. Okay, the user doesn't know what to type until we tell them. So we start with a cout statement, enter an angle in degrees, and then we have our cin statement that reads in the angle in degrees. Okay, it's now pretty easy to get the angle in radians. We have a single line of code that says double angle rad equals angle degrees times capital M underscore capital pi divided by 180.0. Now I don't actually have to put the 180.0 there. I could just put 180 because I know M pi is a double. But just to make sure that we do floating point division, I put the 0.0 after the 180 there. Finally, we can print our table of trig ratios. Okay, we're going to set width 7 for angle. Actually, we're going to set width 7 for all 4 of our columns. We're going to print column headings angle, sine, cos, tan, and then we're going to, this time we're going to add one extra keyword to our set precision. We're going to call fixed. Okay, fixed means we're going to have a fixed number of decimal points after the a fixed number of digits after the decimal point. So even if there's zeros, we're going to print them. Okay, and so now set precision 3 means I'm going to have 3 digits after the decimal point, and that will make my columns all look nice and even. Then I'm going to cout set width 7 angle degree. Okay, then set width 7 sine of angle rad. Notice that I'm printing the angle in degrees, but I'm using the angle in radians to pass to all of the trig functions. So I'm going to call sine and then cos and then tan. Okay, and here's what our output from the trig table looks like. I typed in an angle 22.5. We get that the sine is 0.383, the cosine is 0.924, and the tangent is 0.414. Okay. Maybe you decide when you write this program that you want 4 significant figures. You could go and just change the set precision to 4 instead of 3. However you want to do it is perfectly fine. You can even change the set precision between printing the angle and printing the sine, cosine, and tangent, because it looks kind of silly to have 3 decimal points after the angle when it's only 22.5 and not 22.526 or something, but that's up to you. Now, your lab assignment for this week is going to be to take this trig table that I've printed with one angle, and you're going to print an actual table of trig functions going through every 15 degrees, say, from 0 to 90. So 0 degrees, 15 degrees, 30 degrees, 45, 60, 75, 90, some of the most useful degrees for most common purposes. Okay, shouldn't be too hard to replicate what I've done here and just kind of copy and paste it with different angle degree values. Okay, so in summary, what we've learned today is to use mathematical functions to format output in columns and to format decimal places with set precision, which sets the number of significant figures, and fixed, which sets a fixed number of digits after the decimal point. All right. Hope that was enlightening and entertaining. And until next time, good luck and happy programming.